the meetup. Noam.
Here, let me do this.
Sorry, we forgot to mic him up.
Yeah. So, thank you, Jared, and thanks everyone for being here and on this sweaty July day. Am I on? Brittany Pack?
The non-Brittany pack. All right, so different.
Here,
Okay.
we're just going to put that there.
We put it in your top in case you move.
All right.
All right.
Sorry, folks.
Try 3. So people can say that what Docker is, it's different from lighter machine that can be scaled. Probably what interests us most as scientists. But the reason that makes things different, with a virtual machine, your virtual machine has its own operating system, its own file system, its own collections of library, binary programs, of data within, and then the apps that are running in that virtual machine as well. And you on the same physical infrastructure, each of which will have an operating system and their own file system and all of these things together. And that lets them operate as isolated environments. However, it's really resource intensive because each of them needs to host machines and all of that CPU. Thing through a much lighter weight infrastructure. So first of all, in Docker, all your virtual machines share the same operating system. And there's sort of an agreement from the start. All Docker isolated environments are Linux environments. So that's sort of like a decision made from the start. Everything works. You don't have to host multiple types of operating systems. But actually, they're all simultaneously operating the same running operating system or kernel at the same time. So your machines can share that. They can also share components of their file systems or their software libraries or components of the software that's installed, even though they're isolated or running environments with their own memory and their own apps. And for that reason, you can run a lot of Docker containers on a lot less infrastructure, and they're able to start up and down faster and be orchestrated as a group much faster. Now, this in and of itself doesn't make it useful for a person whose job is primarily to analyze data in their own environment. You're not necessarily building things to create a map across the world. But the fact that it's become so popular amongst all of those people has made Docker kind of ubiquitous. So Docker can scale. It's used by so many organizations at this point. It can be a standard for isolated environments that lots of technologists use. And that means that you get weird images like this, which is from Amazon Web Services Docker Orchestration Hub, in which you get to be the captain of Deep Space Nine, moving around a lot of ships, containers, and those containers are all, on one hand, isolated environments, but the other reason that sort of container metaphor works is they're also things that can be moved around and lots of people can use in lots of different places. The ubiquity of the Docker container as a standard means that an isolated environment that you create is an isolated environment that can run on somebody else's computer or lots of times over thousands and thousands of computers in a bigger circuit. I want to jump right into actually running some things and showing some examples, but first what I want to do is make sure we all have sort of a bare minimum of understanding of vocabulary and actions and commands. So in Docker, there's a thing called an image. An image is the wrapped up package of everything in a Docker environment. It has the files of the operating system, the declaration of environment variables, and other things that might affect your work. That's the package, and the package that can move around. When you take that package and run it and create the machine that's running in an isolated environment, that's called a container. So you have an image that's static and a container that's dynamic. There's also something called a Docker file. A Docker file is merely a script that runs a series of commands that creates an image. So an image can be a big thing. It's megabytes and gigabytes of information because it has all of the file systems, all of the installs. The script is just what pulls that together. It can be just a short series of commands that define these dependencies inside it. And then there's something called Docker Hub. Docker Hub is a service online where people can share Docker images. And one of the things about within it. Docker Hub is not the only place you can do this, much like GitHub and GitLab, and you can have private instances and do it on your own services. But Docker Hub is by far the most ubiquitous and widely used and sort of the default that most people go to when they're sharing things, at least for images. So that's the object we think of. Then there's the actions. So I'm going to give a bare minimum of commands. Docker is a lot like Git. It's a program that you're running on your computer. Everything you do starts with the word Docker. Then there's a series of verbs and then a million that can be uninterrupted and changed. But ultimately, you're really only doing the primary actions and start out with just this short number of them. By the way, all the slides will be up in addition to my talk, and I'm also going to have a bunch of code up there for you to see as well, so you don't have to worry about examples too. So there's Docker pull, which means you're going to get an image from another repository, or maybe your organization's private repository. There's Docker build, which is to take a bunch of other files, that Docker image to give it a name so that you can and use it again. When you have an, you can, if you put, say, Docker, give an image name, it'll set that container. And because the container is an isolated environment, you usually have to specify how you want to get data in and out, you want to communicate with it. And for that, there's usually specified you get to communicate with the machine with, which is sort of how you communicate via network. Or you can just share it between the isolated computer running inside it. You might specify some other commands about what you want the image, or it'll have a default one. And you may or may not say detach and run the container in the background or in front of you as it's going. And then the container doesn't, it has a short. There's Docker. There are 1,000 other Docker commands, but this is probably most of what you're going to use. And you're probably going to use a subset of these, because one of the nice things about Docker run is if you specify, it'll for a pull, or if you specify it, automatically build if it hasn't been built already. So it really comes down to very working with. These commands are generally run in a terminal with R, and all of these things can be done in R as well. R being R, there are at least 3 packages for running Docker. Surprisingly, I mean, they're all pretty good, and they all pretty much do the same thing. And the API for them is not that different. So I don't have a really strong recommendation as to which one you use. I like this one called Stevedore. It's partially because my friend Rich Fitzjohn has written it, partially because it has some particular small advantages that I like, but it's not super important. Most of these things work the same. So to do all of the things that I just described that you would do in the terminal, you can do it in R by loading the Stevedore library. You start what's called the Docker client, just so it's communicating with the Docker software. And then, just like in the shell, you can pull an image with an R function. You can build an image with an R function. You can take an image and start a container with it, specifying your parts and your volume, your command, and you can stop that container. And you can do that all in your R console or your R scripts as well. So why would you actually use this? This is actually the part that I think, like most introductions to Docker, kind of skip over, because they assume you know why you're using it, or they assume a particular reason for using it. And that can vary a great deal whether you're a person who's using it to build a web service or trying to package a scientific analysis, all of which you might be using in R. I sort of break these up into 4 major categories of how you might be using Docker. One is largely about reproducibility, to build a working environment that you can be sure that things will run the same way in from place to place. That's one of the sort of core R reasons, reproducibility. But you also might be using Docker to run a different program for R to access, to call. You might be using Docker to run an R thing that you want a different program or service to call. Or you might be using Docker as a way to ship around your sort of intensive compute jobs so they can be run on different infrastructure. All of those things share some components, but they're different sort of patterns of working. if you're working in a fixed environment, what really matters is what's inside the container on top of the whale. So what you want when you're working on a primary R analysis within a Docker container is to have all of the tools that you want to do your data science process, your analysis within that, be it R, RStudio, the data, the extra libraries you might be using. And you want all those all packaged inside in such a way that they're like locked and they're a time capsule. And your colleague or yourself 6 months from now, after you've upgraded your operating system, can run those things. So it's really just, it's the lockbox in this case. When you're doing something like this, you have, let me skip. This is an example of why you might want to use something like this. So this is a screenshot repository of mine associated with a bunch of work we did in EcoHealth Alliance and published a paper associated with it. And we tried to do a really good job of making it possible for other people to also run this, okay? So we made a makefile so we could run one command to do all of the different components of it. We used packrat to save our R packages. We had extensive documentation. You see the bottom of the description of the file tree of what all the files are. And as I was writing it up, I said, okay, well, you need all these packages. We have packrat, and we have the makefile, and we have this description. And also, you need Cairo and GDAL and Geos and Magic and Java and curl and PNG and all of these things. And at the time, I did not think to put the version of the software on. We did manage to run it on 2 different computers, so it did actually happen at a certain point. Kale is in the back smiling there because his laptop was the one that took a couple of days for it to happen on. We sort of had to shift around the pieces, and I don't know if we wrote down everything that one needs to do for this. And then you end up with this problem, which was really well outlined by this paper last year in Nature Biotechnology, where even if you get the thing to run, people have slightly different versions of the software, and so someone gets a result where you get significant results, and here the answer is 223, but then someone tried to run my software and they got 228, and you're like, oh no, you have to downgrade because there was a bug that we got around in this way, but if you use the bug fix, then you're going to get something someone else didn't on Mac rather than Linux, and they get a different answer. What you'd rather have is everyone running the thing in the same box. So the tool you have for that, for our users in Docker, is this great thing called the Rocker project. The Rocker project was started by Carl Bettiger and Dirk Edelbatel. Carl is one of the founders of ROpenSci. Dirk you may know of as the creator of RCPP for putting C++ programs into R. They've created this great project where they have a huge number of R-based Docker images that let you run lots of different configurations without having to design the whole setup themselves. What they do is provide a whole library of Docker images that have different sets of packages installed, different associated operating systems and system libraries, and they have it for every version of R going back 5 years, going back to each patch version. So all of these stacks, like you may want just base R, you may want R with RStudio installed in it, you may want R with all the tidyverse packages on it, and you may want that for R 3.3.2. And you can just grab any of those off of Docker Hub under the Rocker org organization in order to run that particular image. And then you can modify those for your particular without going back and doing all of the startup components. So let's take a look at how one actually does it. So I have an analysis that's very important. Done a lot of important research to show that there is a relationship between GDP and life expectancy in the world, and I want to make sure that anybody else can run that, and that I would be able to run that in 6 months from now, or can run different infrastructure that I'm currently doing now. So I have a script that defines that. Most of us know that. We have a script, maybe a Git repository, maybe a set of data, all of these components that we need to reproduce the analysis. We also have to define the environment. So what you do is add a folder a Docker file. So the Docker file is just a series of imperative commands to define. It's a very simple Docker file because it only has to do a couple of things, because we're going to start the Docker file by saying we're going to use as our basis for it, using the from command, the rocker tidyverse 3.3.2. So I'm going to have an image that installs R and the tidyverse, and it will use version 3.3.2 and all of the versions of the packages associated with 3.3.2. I have one command that just means tagging it with my name so that people can know where this image came from. And then I have one command to install a dependency. So I use the run command to run a line, which is just a shell script, which is install a package, because Gapminder is the package that is not in the tidyverse, but is part of my analysis and I need as a dependency. And then the final line is just to add the file, analysis.r, into this Docker image. And we're going to put it in a folder called home RStudio. So everything I need to run this that can be shipped around is defined in this Docker file. And all I have to do is build my environment with a few Docker commands. So the Docker build command here lets me build, tag the image as my analysis, and just specify the folder that I'm doing, which is example1 rocker. And if I get this right, nope, wrong one. Can run that in a terminal, and what it does is each of these steps. So grab the rocker tidyverse image 3.3.2. I had previously downloaded this and I have it on my computer. If I hadn't, it would have pulled it from Docker Hub. I wasn't sure about the Wi-Fi connectivity here, so I put all these on my computer ahead of time, but just pull that thing down. And then it goes through each of the steps. It adds the maintainer tag, it runs this script. Once again, I'm speeding things up by the fact that Docker automatically, having built this before, is saving these build commands in a cache. And so if I didn't have that, it would actually see that, the installing package component. And then I add the file, it builds the image, and then it tags it. And I called it my analysis. If I don't give a subtag, it always calls it latest. So I have an image, and you turn an image into a running container with Docker run. So I can run this Docker image with Docker run. I'm going to attach it to a port. This says make the 787 my port 8787, and run this thing called my analysis, and run it in the background. So I run that. It gives me a very long tag, which is the name of the image. But if we use the command docker ps, it will list Docker containers running. And in addition to a long, confusing hash for the name, it also gives a name, in this case, priceless colon. Docker always gives an adjective in the name of a scientist to give your containers unique names. And so that just got fired up 11 seconds ago off the my analysis image. And it has port 8787. 8787. And we are placed into an RStudio environment. So you can see that we are running our 3.3.2 here, which is different. My computer is running 3.5. It has the tidyverse packages and the Gapminder package. It has, and so I can run everything in here exactly as I ran it elsewhere. And if I ship this image to somebody else, I push it to Docker Hub, anyone else can run this the same way. Now, build things get more complex. So that's the nice thing about the Rocker project. It has all of these pre-built images that have most of what you want. But there are a bunch of other interesting tools for getting your Docker file environment together, particularly for R. So one of these is the containerization package. Containerization package scan your directory of files or load your session info, figure out the current version of R that you're running, if there are system dependencies of those packages, and write a Docker file for you. So you just read your session info, it writes that Docker file, that you can just build that image, and usually it gets all the defaults right for you. It grabs the right Rocker image as the base, and it has all the components for you. So that's super helpful. You don't have to write every Docker file. There's another version of this specifically for R Markdown documents. If you don't want to have lots of files lying around, you're just trying to compress everything into one file, there's a package called Lifter. Lifter just lets you put all your Docker associated metadata in that YAML header of your Docker file. So in addition to your title and author and date and what it looks like, you just have a Lifter field, and you can say, what your basis of your Docker file is, whether you need pandoc to build things, whether you need tech to build things, and what your system dependencies are or packages installed from different repositories. So that too will create a Docker file, and Lifter has a command render Docker, which will fire up the Docker file, run the render command, get your output, shut it all down, and then rather than just knitting or rendering your R Markdown in your current environment, it's happening in the environment. It's defined in the header of the file. So it tries to get all of that sort of Docker workflow into just, that button that says knit at the top of. Those things both help you at the end of setting up your Docker environment, but you also may want to distribute it. And there's this fantastic tool called Binder. Binder was originally designed for distributing Jupyter notebooks, but does RStudio or all sorts of other environments now as well. I don't remember exactly how they fund this, but if you have a GitHub repository with a Docker file in it defining a Jupyter or RStudio environment, Binder will simply launch a server running that image for you for free. It's not the like most resource extensive one, but it's great for letting anyone else toy around with analysis that you have. And so if your analysis is open source, for instance, we published a paper on ecological noise phenomena, and he just has a link in here for launch Binder. All that does is send Binder the URL of the repository. And so this is just a badge you add to your repository. You do that, it takes you to Binder, it will fire up the repository, it's pulling the image, it launches a server, and in a minute here, you will end up with that same RStudio environment that Carl used to do the analysis that he used to publish that paper. And so this here is his research repository, the version of R that he was using, all the packages that he was using, including custom ones, and you've got the paper itself as an R Markdown file that you can render, or you could grab the code and do it yourself. There's sort of layers to this, in that you could grab that code and try to run it on your own computer, but if it's not working for you and it's a dependency problem, this lets you get there instantly, and you don't need any infrastructure. And it's a great example of you're really deploying this reproducible container as a service for people to use. I'll give you another example of how you might try to sort of package up a work environment. Maybe you want to create a container that is common for the tools and the problems that your team is using. So at EcoHealth, we have a container called Reservoir. Reservoir is based off the geospatial Rocker project, but it has a bunch of other machine learning and a bunch of other sort of communication tools within it. It runs on our high-performance server. It also runs on our new high-performance server, so I didn't have to configure that server. I just moved the image over, so the same thing works there. If we need to spin up an environment with different resources on Amazon, if our local stuff goes down and we need to move to the cloud, the container is available to use. So it has sort of the things we commonly use on a day-to-day basis, and if I need to update it, I can update that in the Docker file, and then rather than like bringing the server down to do it, I like make sure the Docker file builds, run in a different place, and then when it's working well, I just shut down the old image and start up the new one. And so that makes sure that we have a common environment that we could work in different places, And it's also a good way to manage a common working environment for people. This reproducibility box isn't actually why Docker was really originally designed, though. Docker was designed as a way of firing up and delivering services in sort of rapid ways. So one of R's great advantages is its ability to work with things that are not R. When S was created, the idea was to provide access to compiled statistical libraries in Fortran and C. And as time has gone on, R has had a lot more connectors to different types of things in Java and in Python and to web services. And you can think of Docker as a way to package up anything that would run in a Linux box as a service that R can call. And so you might do this sort of a custom, as for a custom service yourself. You have an API that you want to run locally that R can connect to. And then there are also packages that are specifically built around the idea that there is a service or a server in Docker that you want to run. So some of those include browser rendering services for web scraping. So Splasher and Selenium are both frameworks for web scraping that have a server that's running a headless browser and a series of commands to control that browser and a bunch of software to render and transfer information from that browser for either testing apps or web scraping. So those live in a Docker container that an R package calls. There's another neat one called the open source routing machine, which is basically a sort of a Google Maps route finder using OpenStreetMap data. So it's a series of libraries that live in a Docker container that you can communicate with. They have a version on the web. You can call it, the website, but that's slower and they have only so much capacity. But you can just run the whole thing locally on your machine to pull those routes. And then, machine learning services like H2O, if anyone's familiar with using H2O is a Java application. Java applications can be difficult to get configured properly and deal with installation, but you can run H2O in a Docker image and do all of the same things, and you don't have to, work with different versions of Java installation. So if we're to use Docker to run something like a web scraping service, we're not building an image. What we're doing is we're pulling an image, using and communicating with that image, and that image has nothing to do with R. Itself doesn't have R installed. It has whatever Splash has, which says some combination of Python and something else. I don't actually remember, and it doesn't really matter. So if I want to use something like this, I can load up my Stevedore library to control Docker containers, and then the Splash R package, which is what communicates with the server, a Docker client, and then I just create a container, have the local, or will be pulled from Docker Hub if I need it. I say which ports to open. I say that container running on my machine. With sort of Steve, you can query the container to ask about it. You can get, that it's running, the name, whatever Docker called it. You can issue commands on the container that way. And now the commands in the Splash package, they are just sending HTTP requests to that container to tell it what to do and get information back. So this is an example where we're visiting a CDC website that shows flu cases. So you have to get to the website, and maybe you want to get this graph, but you have to get past this disclaimer, and you want to display. With Splash, that we're running on our local computer, we're at port 8050, because that's what we opened up in the back. Sort of whole type of command, fire it up, go visit the web, press enter, and so when I run that, R is just sending commands back and forth rather than to a server on the web, to a server running on your own machine, this sort of microservice. And it's waiting a bit so that the CDC it can load, but it just is, in the end, will return the image of the website that I'm looking for. And you might be doing all sorts of other things, grabbing a table, scraping the data, processing it. But rather than installing Splash and its Python dependencies, all those things, we run Splash in the container. When you're done, you can stop a container, You can check that container has exited. And I actually made this thing a little more complex than I need to for demonstration purposes because the Splash package itself just has a command start splash that does this. And if you look inside it, they're actually using the Docker and the Stevedore package, but the syntax is almost exactly the same. It's firing up the client, starting the image, and returning that. So you can run all of that. And then there's a stop splash container that does the same thing. So that's what you do when you have R on the outside and another service on the inside, like this, where you want to call all of these other programs that you want to package up and not deal with installation. But then you can go the other way around. You can have R inside a box, and then you want to deliver services or data or other things to a different program, to a website, to a different framework where people are pulling data from, or just sort of deliver your data sources or your models especially to some larger software framework, some larger app or web service that needs to call your R program, but R is not part of what your web services team works with. But a Docker package is what a web services team could totally work with. They're like, oh yeah, we can run that. It's on this port. When our Python or JavaScript or other components need to call this, they'll just ask the question on the port, we'll get the number back, the predictor, the chart that you generated, any of those things. And so there are a bunch of different types of R services you might create. Probably the one you're most familiar with, or most people are most familiar with, is Shiny. You generate a web app. So you can have a web app in a Docker container that can run anywhere. There's another similar framework called Fiery, which is like a much more low-level, unopinionated way to generate websites from R. Or you might not be delivering an interactive user-facing thing. You might be delivering services and REST APIs for a different group to work with. And you can do that with a package called Plumber, or another one called OpenCPU, both for developing REST APIs. And then what we did before, showing the RStudio environment or a similar Jupyter environment, those are sort of environments delivered as services as well. So, in addition to just having that packaged product, you are delivering a service of letting people work on it for you as well. So all of these things are different ways you might want something that is R running in a box that can move around that other people can access. Let's see if I have this right. If we wanted to I stole this one from Flop. Sort of a typical Shiny program, we have a bunch of library calls at the top to define what we need. We do some pre-processing of data. There's a user interface component and a service component. In this case, the Shiny program just demonstrates some of the interactivity and crosstalk that you can have between data tables and Plotly. And so you put that all together, it exports a Shiny app. Shiny app will run fine on your machine. How do we get that Shiny app to other places? Well, once again, we define a Docker file. So in this case, again, I'm going to start the Docker file from tidyverse, so I have all those packages available, tag it with my name, and then install the packages used in the Shiny app. So I have DT and Plotly and Crosstalk. You notice I have Shiny itself here because I have this other line which has a sort of confusing component. And this comes from the Rocker project itself has set up a command that installs Shiny and all of the Shiny server dependencies, so you can add Shiny to any of the Rocker images. So you might want the tidyverse image with Shiny. You might want the Debian Edge version with Shiny, or you may want an older version with Shiny. So you just run this, add this command, which is in the Rocker documentation. You get Shiny added to your package. And then you import your app itself and put it in the Shiny server's serving directory. So we can fire this up. This time I'll do it from R rather than the shell. I load Stevedore and the Docker client. I'm going to build off of the Shiny directory and call it shap. it runs all of those commands. So now we have a built image, which we call shap. And then we can run shap as a container and go to it now. So the Shiny container on port 3838 is running this Plotly app, which has a talk package that lets you do interactive selection. And so if you're building something that's going to, a user-facing, this can be in a website. Maybe it just ends up in a, in a frame within a larger component of your organization's site. Or maybe you're like, well, I've written this, but I have no idea how to deploy it. What if it has to reach a whole lot of people? Sort of a development operations group can just take this and like, oh yeah, we can set this up so it can scale. And there'll be 1,000 instances of it. So every time it gets to have too many people, we'll fire up a new one. All they have to do is run the Docker container and have that triggered as it needs. And stop that. I have another demo here of Plumber. If you're building an API where you want to serve predictions or data, Plumber's are relatively, it's been around a while. They've really only invested in recently. It comes from Jeff Allen, who's at our studio. It lets you define functions that will act as REST API endpoints. So you can send echo to this service, and it will return an echo of the message saying this message is, which is not super exciting. You can send plot, and you'll get a random plot. You can send sum and parameters and add some numbers to it. But if you can write a function, you can write a function that generates predictions from your XGBoost model. And so someone who's querying the service to generate a mop saying, what's the prediction of the best pizza restaurant that you're looking for, you can just have a function in R that does that, deliver it as a service. And then, of course, we want that service to integrate with someone's site through being a Docker image. And so we'll just pull the Plumber Docker image that has all of the Plumber dependencies in it, tag it, add our app. This is a particular modification of what the startup command is in this Docker image, which says fire up Plumber. And I just added this because it lets me add this Swagger command here, which automatically generates Swagger documentation for my API. And then we run the app itself. So in this case, we'll put it on, let's see, build it here, put it on a port. I guess I ran it twice, so it says port's already allocated because we already have one. So I'm writing this one at port 1000 is festive Chebyshev. And if we visit that, I have a web service that delivers an image. Every time someone calls this API endpoint, refresh, we have that R process running. It's returning an object to you. You can also say add with parameters A equals 3 and B equals 5, and you get this very, glad you're here, not add, sum. It's a very exciting response. But it's the same service, and no one cares what's running underneath that service is the main point, and no one cares exactly how to install the thing. So you have both the output and the startup are just pluggable in sort of anyone's web infrastructure. Finally, let's see. If you're, just like with Lifter or Containerit, if you're building a Shiny app and it has a bunch of dependencies and you want to create a complex Docker file to make sure all those pieces are there, the Ryze package does that for Shiny apps. It finds all the pieces necessary for the Shiny app to run. It assembles your Docker file. You might have to, all of these you might have to tweak, or maybe you have an efficiency improvement, but they give you a really great start. The final thing you might want to use Docker for is deploying big compute jobs. So Docker container is something that can move between infrastructures. And so if you have a big job that needs to use a bunch of different cloud services or a bunch of different computers, you can send that job in the form of a Docker file and get the results back. And so if you have something that really needs to scale up in terms of compute, Docker is a way to do it. Often you don't have to build the images and send them because that infrastructure has at least Docker installed on it. So you can build and run the containers there rather than build them and send them along. I'm not going to go through a detailed example here, but this is one I was actually just working on the other day for some of my own cluster stuff. If you're familiar with the future package for parallel computing, it's a really sort of great framework for sending jobs to any background process and getting it back. And so I had set up a thing where I made a cluster of multiple computers on my network, and then it has this one parameter called rscript, and normally that just says what's the command to run R on that machine, so when we send the commands, we can run that command on that machine. Rather than having a path to R itself, I said run a Docker image and run R. And so when I send a job to that, it will fire up the Docker image, run it there, and send the results back. So it's something you would send a big job to. You don't want to send something, fire up a Docker image, add 10 numbers together and get them back. But if you have something that's long running, this is a good way you can just integrate this into something that you might already have sort of a standard. Say, no, send it to that computer and use Docker to run R rather than on my computer to do something else. This works with a lot of services. The future package itself has like templates for doing this specifically already with Amazon Web Services and Google Compute, and it probably works with Azure, and I should probably figure that out at some point. There's a package, Google Compute R, that has like pre-built Docker templates for Google Compute R's Docker service. So you just like send this Docker template with this one additional component to the job, and it'll build the image, fire the job up there, and get things back, which is really great as well. If you are deploying big jobs, there's actually a very similar alternative which you might want to consider. There's a program called Singularity that is a very similar portable container setup to Docker. It's sort of specifically designed for this big compute delivery service kind of thing. Some of the important differences are that you don't need admin rights on any machine to run it. So, it might not just be that on some machine you can't install R, you also can't install Docker, and it's not pre-installed. You're using someone's cluster or supercomputer. You can pull down Singularity and run it as a user with no. They're not isolated for running a service. They're designed for running a workflow or a batch job or some utility one time. And so they tend to have access to the file system. Someone said Docker is like an alternate universe, but Singularity are parallel universes that have occasional shifts in the timeline. So it's more like it'll take your current machine and pull out the operating system and put a different one underneath it. I haven't actually used it, but the important thing is it can run the Docker images too. So you can grab a Docker image and run it within Singularity. You don't have to build up everything from scratch. You can still use the Rocker project or something else. But I put it in because when I posted this today, Henrik Bengtsson created the future package and does a lot of big compute genomics jobs. San Francisco State doing biomedical work. Said, doing the big compute stuff is a lot easier on Singularity. So it's not my endorsement, but it's definitely a possibility because other people like it as well. I'm going to post the slides and actually a whole bunch of links to the different things that I talked about online as well. So there's going to be a lot more than this. But Docker has really great and comprehensive documentation. You have to remember that it's written primarily for people who are building web services and doing large container orchestration. So they're not necessarily thinking about the data scientist's role when you're doing it. Up inside put together a which is more role. A couple years not everything you do there is necessarily the same you do it now, but it's a good introduction to the process and it has sort of good walkthrough code. And then Like I said, everything will be up tomorrow at my GitHub with New York Docker Talk. So thank you very much, and I'm happy to answer questions.
Thank you. I have two questions to go with. I'm an old friend, so I've written my own thing that doesn't use containers or doesn't use virtual machines as an alternative. So I'm excited to work at Singularity as well. And I'm wondering if you're aware of other projects that use the Docker images or Docker files as configuration of something like containerization.
I mean, it's hard to, like, in terms of other, I mean, there's a huge number of projects that are using
the same like Docker file. Is any other container software able to read the Docker file and build things?
I think only Singularity does, if I have it right. Vagrant works with Docker as an orchestration package, so it will run virtual machines, and it will also run Docker images, so it's a more general thing. Then there's also, like, there's all these add-ons to Docker machine that are sort of various, and then there are sort of whole Docker operating systems that are for configuring the sort of multiple. But I think only Singularity will run Docker images. There or container creation so that containers will be interoperable. That I've followed enough, honestly, to tell you if there's any more than that.
Okay. And then, can I ask another? Okay. I'm wondering if you consider, since it sounds a lot of reasons after using Linux a lot, have you considered app image flat app or snaps for the reproducible, which does it's not a container, it's I think snafus, but
I don't know what any of those things are. Yeah.
Anyone else? All right. Pass it back.
I've heard a little bit of people. Sometimes it's helpful to like load the configuration into your working environment. The conflicts with the servers that are running our studios. Maybe the collaborators want to all have the same version of everything. Is there any way to load configuration from like a Docker image to your working space on your actual machine?
Let's see. Not necessarily load what is like the Docker environment into another environment per se. There are things you can share between your computer and the Docker environment. So you can share directories between Docker and your computer. So you can mount a directory and say, this data directory, this project directory, when I run, say, RStudio or Jupyter in Docker, there'll be a folder there, and that's the folder that's also on my machine. So, like, typically what I end up doing if I have something that sort of has a Docker environment is I'm running RStudio through that, and I run that through the browser, but I'm running on files in my machine. It's just that I'm running those off that. Moving sort of the environment component out, I don't think you can do, sort of, because that's what's sort of in the isolation. So you use that environment on other projects that live on your machine.
So then when you start working with development, you do start the Docker file first, and then you're developing Docker.
I mean, honestly, what I typically do is I'm running locally, and then I run it also in the Docker container to make sure that everything is appropriate, right? So like, I can be a little fast and loose on, the ongoing basis, but, before I want to commit it up, before I want to transfer it, I'm making sure things are running in the Docker environment, because that's the standardization. And so you might do that interactively, or sort of a common pattern is just to use a Docker-driven command to run your tests. So all the tests occur in the Docker environment, and you get them back, and that's fine. And you don't necessarily have to be running the image all of the time in your ongoing sort of development.
I'm wondering if there's any library or anything to running networks on the Docker environment.
So it's a lot less than sort of a virtual machine. One of the biggest things it used to be, and it's gotten much better, that movement between file systems, and so mounting the Docker file system on the Mac file system meant that reading and writing lots of files got particularly slow. That's less the case, though it's still a little bit one of the bottlenecks. But the thing is, you don't have separate memory. Like, the thing about the difference between Docker and having like a total isolated virtual machine and this, which is actually just isolating processes, is that really lowers the overhead on things related to like RAM and CPU access, and so you really don't get much of a penalty at all. I've been trying out some cases recently with looking at GPU and making sure that Docker on GPU machines runs well, and that's like all like at least well over 95% of what the performance is on the raw machine. So that's that's the reason this has become popular. It's like that overhead problem is what people wanted to solve in order to be able to scale things up. I guess it really depends, like how much you care about performance and, sort of what like if all performance is all you care about, right? Like, your optimization space like is all over towards performance. There's a little bit, but the performance hits are pretty minor for the most part. Really the case with specialized hardware is the case where you're more likely to run into that. So, it's a matter of priority.
Anyone else? Everyone just sort of done? Right. Well, Tom, if we can like here. Okay. Only with no one else, Tom, you fit that thing on.
So if I remember right, and I'm not sure about this, Gabor Zardi, who's a member of our studio team and the creator of a huge number of packages, one of the things he did is when he was building a project called RHub, he built a database of all the system dependencies for packages on CRAN. And so, you go to a CRAN web page and it's like you need libxml2-dev in order to install this package. And so it was a matter of like scraping all those files and building that database and maintaining it. And so that service use at this point. So when you get a package, you can query the RHub database, if I remember this correctly, and that's how you get system dependencies that you can install in a standard way through apt-get on, on Linux, Debian, or Unix.
All right, we got my interest up. I imagine a workflow where I want to run a Dockerize on my Mac. Right? So it's Dockerized, so I set it all up, and I get to the point that I'm ready to run, what we refer to in the industry as a big-ass simulation. The last simulations have already run, so we've proved that our logic is right, and we're ready to run the big one. So I want to send the big one out to AWS. But like all my data and junk, I don't want to go through like Docker Hub because it's proprietary. Mechanism by where I go, okay, I got this thing local. Now I want to get it over on AWS. Now I want to do a public portal. How does one do that?
Right. So there's lots of ways. So right. So one option is that you just pull like the Docker. You don't need wherever you have those things, right? Like at some place is the place you have the code base, right? So the private repository where you have the code, you're also pulling in data from other places. In that private repository with the code, you have the Docker file. And so the first thing you do for big ass simulation run is build off the Docker file and run it. And you just have to say Docker run that directory, and it will first build the Docker file and then run the command, essentially. So that's option one. If like building the thing takes a long time because you have a big ass compile before your big ass simulation, then right, and you just want that compile to like happen in the build stage, then you probably in S3 can store as a blob the image itself. right? And then you can say pull the image from blob or my paid Docker Hub account or anything along those lines. And you're going to pull down that image, which might be, like 3 gigabytes of system dependencies and, operating system, and then run it. Yeah, and you could also put the data in that image too if you want to say building the image includes importing the data as one of the commands, and then you can move that around if that's not sort of as active a portion of the simulation. Yeah.
Let's say you're using Docker for analysis. You spun a Docker image, you're doing the analysis in there, maybe you store your data in there. What do you do with generated artifacts from the user? Assuming you're not using volumes that goes to the local hard drive, you sort of want to keep it in the image. How do you go from generating Flash or HTML or this new data sets off of the regular?
So you have a workflow, and we're talking about an interactive workflow, and not just like we're running a pipeline and it's coming out.
Documents, we could use it.
Right. I mean, I would say, like, you have your spun up Docker environment. People use that spun up Docker environment, and then, like, if you were working in an interactive context without Docker, we're just there, we just have slightly different versions of R, then you have to have a place that you can push those to a common hub. It can be GitHub, or maybe you're producing things that are, big blobs, and say we have an S3 storage container that we share, and so when you're done running your analysis, you push up there. If you're not mounting the local volume, you have to do that, because otherwise when you shut down your Docker image, it's going away. Or you run off your, when you fire up, you're running mounted with a local directory, and even when you shut down, those files are still there. But if you have an interactive workflow, then you have an interactive step of sending those outputs someplace as well. And so you sort of have to do that same thing, be it in a Docker environment or not.
Anyone else? Last one? Katie? A lot of repeats.
Does Docker Hub support branching like this, or is it like always just a master?
So you have different. You can have different versions in a given repo. So I'll give you actually the best way to do this is if I go to Hub. Let's go to Rocker. Let's say R versioned, right? Rocker R version is the repo. Within that repo, there are all of these different versions of it, for all of the different R versions. It's not forking per se. There are two ways to get an image, different ways to get a different Docker Hub, or maybe 3. You can have an automated build, which points to a GitHub repo or something similar, and that's just pointing to where our Docker file is. And Docker Hub will automatically run that Docker file, build the image every time it changes over there. So I keep a Git repo, I can add different subfolders or branches, and I can say, for each of those branches or repos, build something and give it a different tag. Also, you can just build something and push it, and you can give it a different tag within the same repo. So what Rocker does and what I do is actually, I use a different CI service. I use Circle CI. I push up there, I run the image, I test it, and when it's done, it pushes it to Docker Hub to make sure it's there. And there's 2 versions of those, because I have one of those that's like GPU enabled and one's not GPU enabled. So it builds both of those, pushes one with the GPU tag, one without the GPU tag.
Okay, then another big round of applause.
I will.
You got some more questions there. There are 4 pies left. I expect everyone to be eaten by the time they all leave. Ryze, Exhibit 6. Paul, JB, Becky, Noam will show the way. Once they get there, we'll show the way there. So they'll be your Pied Pipers. And I'll see you all next month. Thank you.
Thank you, Jared.